Hello everyone, my name is Jiani. I'm currently PhD candidate at Caltech. I'm going to present you prediction of ambient PM2.5 components in Southern California using machine learning. The composition of PM2.5 is complex, and the physical structure, chemical composition, and the source of its components are different, resulting in its pathogenic mechanism is not clear, which determines that it is difficult to best quantify the most harmful aspects of PM2.5 to health from the level of PM2.5, which requires us to conduct health risk assessment at the level of PM2.5 components. As a compound pollutant, PM2.5 contains various toxic components, including water-soluble inorganic ions, carbon-containing components, inorganic elements, and organic matter. Therefore, it is important to monitor the PM2.5 chemical speciation. In 2000, the US EPA launched the National PM2.5 Chemical Speciation Monitor Network to access long-term trends and better quantify the influence of various sources on PM2.5. By 2005, the network had expanded to over 260 sites, where advanced high-resolution instruments exist. Their prohibitive cost-intensive maintenance and the need for the specialized operators make widespread deployment economically and logistically infeasible. To bridge this critical divide between monitoring capacity and public health needs, this research proposed the development and validation of a robust machine learning framework designed to transform sparse, delayed measurement into the actionable real-time intelligence on air quality. So we have two monitoring sites in our targeted research. So one site is seated in the North Main Street in downtown LA, a representative of urban area primarily influenced by direct emission. The second site is located 60 kilometers inland in Ruby Docks, an area typically exposed to aged photochemically processed particulate plume transported from the upwind region of the western and central LA. So here's how the machine learning framework works. First, we have data sampling. The algorithm creates multiple subsets of the original data through a process called bootstrapping, where each subset is generated by the randomly sampling the data with replacement. Second, we have decision trees. For each subset, a decision tree is trained. However, instead of considering all features at each split, the algorithm randomly selects a subset of features. This helps to reduce the correlation between the trees. Finally, we have voting and averaging. Once all decision trees are trained, the final prediction is made by aggregating the results from all the trees. Next, we will apply tenfold cross-validation, which is a technique used to evaluate the performance of machine learning models by splitting the data into tenfold. Here is a step-by-step explanation. I'm not going to explain that in details. Our input variables, we have PM2.5 as the predictor, and the input variable including EC, OC, ammonia, sulfate, nitrate, alumini, silicon, calcium, and iron, titanium, soil, sulfate dioxide, and NOx, ozone, NO, NO2, carbon monoxide, temperature, RH, boundary layer height, wind speed, wind direction, fireworks, and Wi-Fi. So overall, the meteorology, gas, and PM2.5 scenario generally has higher R-squared value for the most chemical components, indicating better predictive performance when using a combination of meteorology, gas, and total PM2.5 data. The meteorology and the gas scenario often has the lowest R-squared value, suggesting the total PM2.5 as an input is very important for the overall prediction. The gas and PM2.5 scenario shows moderate performance, with R-squared better than meteorology plus gas in some cases, but not as high as meteorology plus PM2.5 or meteorology gas and PM2.5. In terms of the individual PM2.5 component, nitrate has the best R-square in the meteorology PM2.5 scenario, followed by meteorology PM2.5 in both sides. And we can calculate the importance ranking, which provides the input variables most influence the prediction of PM2.5 chemical composition. So first we have total PM2.5 mass, which is consistently to be the most dominant for the overall predictions, and followed by the RH, a crucial predictor, especially for the metals and the organic carbon, and also NO2 as a top predictor, ranking high for the metals and OC, and dominating the meteorology and the gas scenario. We also have a boundary layer height, which is an important influence, often following PM2.5 mass and RH. So thank you so much for listening. You can reach me out through the email listed as here, and also we have published this paper on atmospheric environmental acts, and here is the citation you're welcome to read more for details. Thanks again.